Dear students, today we'll see the fifth part of multiple choice questions on the subject of industrial automation, in which we will see today a few questions on PWM techniques. We will see a few questions on cycloconverters, and we will see a few questions on speed control of motors. So let's start with the fifth part. So question number 81. Which of the following is not a PWM technique? So if you remember the types of PWM techniques, so in that types we had studied single pulse width modulation, multiple pulse width modulation, sinusoidal pulse width modulation, modified sinusoidal pulse width modulation, phase displacement control. These were the types of PWM techniques what we had studied at the end of inverter, because this was a process by which you can make a highly controlled inverter. Okay, so in this question it is asked that which of the following is not a PWM technique. So we have single pulse width modulation, we have multiple pulse width modulation, we don't have triangular pulse width modulation. There is no technique called as triangular pulse width modulation. So here, according to this question, according to the question, option C will be the right answer. So here, option C, we will take it as right answer. So we don't have any triangular pulse width modulation in PWM technique. We have single pulse, we have multiple pulse, we have sinusoidal pulse, but we don't have triangular. So here you can see option C is the right answer. Then we'll go to question number 82. In pulse width modulated inverters, the output voltage is controlled by controlling what? The options are input frequency, modulating index, amplification factor, and none of the above mentioned. So from this, the ratio of voltages of the control voltage and the reference voltage gives the modulating index. So here in pulse width modulated inverters, the output voltage is controlled by controlling the modulating index. So here option B will be the right answer. So here you can see this is option B, modulating index is the right answer. So for that we can have explanation. Modulation index is equal to VR upon VC. So here VR is nothing but it is the voltage of the reference volt signal whatever you are giving, and VC is the voltage of the control signal. VR is for reference signal and VC for the control signal. Okay, so both these signals we are going to give to a comparator, and then the output of comparator will be taken to drive the SCRs of the inverter circuit. Okay, so that is what the concept of PWM technique is. So modulation index is equal to VR upon VC. Modulation index controls the output voltage waveform as it is proportional to the fundamental component of the output voltage. So here the option will be modulating index. So here you can see option B, that is modulating index, is the right answer. Then we'll go to question number 83. The shape of the output voltage waveform in a single PWM wave is. So if you see the shape of the output voltage waveform in a single PWM wave, so we know that when we had our PWM technique, so we used a comparator there, and in a comparator we saw, say this is your a comparator, and then for comparator we gave two inputs. One was your a triangular wave, and the other one was sinusoidal wave. Sinusoidal wave, that is sine wave. Okay, and this is your a comparator. Now the output of this comparator is going to give the trigger pulses for the SCRs used in the inverter. Now how this output will look like? Now here what will happen is the two waves, that is the sine wave and the triangular wave, are compared. They are compared. Okay, and wherever you get the point of interaction, point of intersection of the two waves, that time the output state will change. So output will look like this, it can look like this, it can look like this, it can look like this. Okay, so in that way the output you will get, and this type of output is called as quasi square output. it is called as quasi square output. So the shape of the output voltage waveform in a single PWM is quasi square wave. So here you can see the explanation. Positive and the negative half cycles of the output voltage are symmetrical about pi by 2 and 3 pi by 2 respectively. The shape of the waveform is obtained is called as quasi square wave. So here you can see option C is the right answer, quasi square wave. Then we'll go to a question on cycloconverter. Question number 84. A cycloconverter is a, options are one stage power converter, one stage voltage converter, one stage frequency converter, or none of the above. So in cycloconverter, what we are doing is we are converting AC to AC. But when we are converting AC to AC, the frequency of the input AC can be varied at the output. Varied at the output. So we are going to vary the frequency. So it can be one stage frequency converter. So option C will be the right answer. So here you can see the explanation. A cycloconverter converters input power at one frequency to output power at a different frequency with one stage conversion. So here option C, that is one stage frequency converter, is the right answer. Then we'll go to question number 85. Applications of cycloconverters include option A is speed control of AC drives, option B is induction heating, option C is static VAR compensation. Option D is all of the above mentioned. So speed control of AC drives, induction heating, static VAR, or compensation, all these are applications of cycloconverters. So here the option D will be the right answer, that all of the above mentioned are the applications. So here you can see explanation. Speed of induction machines can be controlled by controlling the input frequency. In induction heating, eddy current is proportional to the square of the input frequency. So all these applications come as applications of cycloconverters. So here you can see applications of cycloconverters include all of the above mentioned. So option D will be the right answer here. Then we'll go to question number 86. The single phase midpoint type cycloconverter uses dash number of SCRs. So here, when we studied the circuit of cycloconverter, and that too a single phase midpoint type of cycloconverter. So in that we saw some circuit like this, that we had a input AC given to a transformer. Input AC is given to a transformer. So here you can have your a transformer, and then here at the center tap you can connect the load. This is the load, okay, and then you have to make arrangements so that the output should be either positive half cycle or negative half cycle depending upon firing of the SCRs. So here we can have two SCRs. Here we can have two SCRs. One SCR will be facing one way. This is one SCR and this will be another SCR. Okay, this will be another SCR and this can be two SCRs. And here on the negative side also you can have two SCRs. One will be having a direction on one side and the other will be having a direction of another side. Okay, so here you can have like this. So here you can have an inductor coil, and here in this way you can show this is the input AC, and across the load you will get the output AC of desired frequency. So here how many SCRs we are using? We are using 1, 2, 3, 4. So that they will be named as P1, P2, N1, N2. So 4 SCRs are used in a single phase midpoint cycloconverter. So 4 is the answer. So here two negative and two positive SCRs are employed in midpoint type cycloconverters. So here you can see option A, 4 is the right answer. So here in the positive half cycle, that is from omega t is equal to 0 to pi, which of the mentioned options, which of the SCRs in the mentioned options will be forward biased? Option A is P1 and P2 will be forward biased. Option B is N1 and N2 will be forward biased. Option C is P1 and N2 are forward biased, and option D is none of the above. Okay. Now, when the input is from omega t is equal to 0 to pi, so if you take that omega t is equal to 0 to pi, so omega t is equal to 0 to pi. That means it is 0 to pi. So this is how you can show the input, 0 to pi. Now in this case, the point here of the transformer will be positive, this will be negative, this will be positive, and this will be negative in a center tap transformer. Okay. So in this case, if you see, if the current starts from the higher potential, when it is flowing from here, P1 will be forward biased. P1 will be forward biased, and the current will go through the load to the negative point. Similarly, when you see the second part, that is, this point is positive and this is negative, so current will flow from here, and if you see here, N2 thyristor will be forward biased and it will go to this point. So in this way, which SCRs are conducting for the positive half cycle? The SCR which are conducting are P1 is forward biased and N2 is forward biased. So here P1 and N2 are forward biased. That is option C is the right answer. P1 and N2 are forward biased. So here you can see the explanation. In the positive half cycle, upper terminal is positive of the upper secondary and the lower terminal is negative for the lower secondary. Hence P1 and N2 are forward biased. So here option C, that is P1 and N2 are forward biased. Then we'll go to question number 88. In the below given cycloconverter circuit, dash and dash conduct in one cycle together. Okay. So if you consider one cycle together, if you consider positive and negative, two half cycles, that is, this is one cycle together. When you are having positive half cycle, this is positive, negative, positive, negative. So in that case, we saw that P1 and N2 were forward biased. So P1 and N2 were forward biased. And when the cycle is negative, that time this point will be positive, this will be negative, this will be positive, this will be negative. In that case, if you see, then P2 and N1 will be forward biased. So if you see the options for positive half cycle, we have P1 N2, and for negative half cycle, we have N1 P2. So in a full cycle, P1 N2 and N1 P2 will be forward biased and those will conduct. Okay, so the option B is the right answer. So here you can see in the positive half cycle, upper terminal is positive of the upper secondary and the lower terminal is negative for the lower secondary. Hence P1 and N2 are forward biased, and likewise N1 and P2 will conduct in the next half cycle. So here you can see option B, that is P1 N2 and N1 P2 are going to conduct in one cycle together. Then we'll go to question number 89. A cycloconverter converts. So this is a very easy question. It is basically converting AC to AC, but it is converting AC to AC at different frequencies. The AC what you are going to get at the output will be at a different frequency. So option D will be the right answer. AC to AC at different frequencies. So here I can see option D is the right answer. AC to AC at different frequencies. Then we'll go to question number 90. PWM switching is used in voltage source inverters for the purpose of, so what is the purpose of using PWM technique? Okay, so it will, options are, it controlling output current, controlling input voltage, controlling input power, controlling output harmonics. Harmonics are the multiples of the fundamental frequency and output voltage. So option D is the right answer. We are controlling output harmonics and output voltage. So here you can see the explanation. PWM stands for pulse width modulation. It is used in the voltage source inverter to control the output voltage and output harmonics. It is a method of controlling the average power of a signal over a continuous range by switching it between on and off states. It is a method of generating amplitude modulation. By increasing the number of pulses per half cycle, the order of harmonic frequency increases so that the filter size is reduced. So here we see that option D, that is controlling output harmonics and output voltage, is the purpose for using PWM switching in voltage source inverters. Then we'll go to question number 91. Speed of DC shunt motors are controlled by. Okay, so if you remember the control of DC and AC motors section of industrial automation subject. So in that, the speed of the DC shunt motor are controlled by. Option A is given as flux control method. There is a flux between the two windings. Uh, B is rheostatic control method, where rheostatic resistance is going to vary and the voltage is going to vary. And C is voltage control method. So here all these are the same thing. All these functions are going to do the same thing. They're going to control the speed of DC shunt motor. So flux control method also can be done. Rheostatic control method also can be used. Voltage control method also can be used. So all of these will be the answer here. Option D is the right answer. So speed of DC shunt motors are controlled by all of the above mentioned methods. Then we'll go to question number 92. A series wound motor is also called as universal motor because, okay, when it is called as a universal motor, then it can run on AC voltage source also and on DC voltage source also. So if a motor is running on AC voltage source as well as on DC voltage source equally well, it is called as universal motor. So here option A, it will run equally well using either an AC or a DC voltage source. So that is why it is called as universal motor. So option A is the right answer here. Option A will be the right answer. Then we'll go to question number 93. In armature voltage control method of or rheostatic control method for speed control in DC shunt motor, a variable resistance is. Options are added in series with the armature winding, added in series with the field winding, are connected across armature winding, both in series with armature and field. So from all these options, it is true that it is added in series with the armature. Then only it can control the flow of current through it. So it is added in series with the armature. So here option A is the right answer. It is added in series with the armature. Then we'll go to the next question, question number 94. Which method is suitable for the speed control below and above the normal rated speed of DC shunt motor? So options are flux control method, rheostatic control method, voltage control method, and all of this. So which method is suitable for speed control below and above the normal rated speed of DC motor? So the best method which is suitable for speed control is the voltage control method. So here option C will be the right answer. Voltage control method is suitable for speed control below and above the normal rated speed of DC shunt motor. Then we'll go to question number 95. The armature voltage control of DC motor provides constant torque drive, constant voltage drive, constant current drive, or none of the above. So here the armature voltage control, the voltage is going to vary, and according to that the armature current is going to vary, and according to that the speed of the motor is going to vary. That we know, but in all this process, the bending force, the bending moment of the motor, there is a torque, there will be a constant torque drive. Okay, so option A will be the right answer, constant torque drive. The armature voltage control of DC motor provides constant torque drive. Then we'll go to question number 96. Which one of the following is not necessarily the advantage of DC motors over AC motors? So there are four options given here: low cost, wide speed range, stability, high starting torque. So out of these four options, which is not the advantage of DC motor over AC motor is low cost. Low cost will become the wrong advantage. So it is not necessarily the advantage. So low cost is not the advantage of DC motors over AC motors. Then we'll go to question number 97. For which types of DC motors dynamic braking is generally used? Shunt motors, series motors, compound motors, all of the above. So for all the motors, we use dynamic braking only. So dynamic braking is used for shunt motor also, series motor also, compound motor also. So here the option D will be the right answer, all of the above. All of the above is the right answer. Then we'll go to question number 98. If the speed of a DC shunt motor is increased, then the back EMF which is developed of the motor will increase or decrease or remain same or become zero. Obviously it will increase. When the speed is going to increase, the flux linkage is going to increase, the back EMF is going to increase. So option A will be the right answer, increase. So back EMF is going to increase when the speed of the DC shunt motor is increased. Then we'll go to question number 99. Torque developed by a DC motor depends upon magnetic field, active length of the conductor, current flow through the conductor, or all the above factors. So here if you see the four options, magnetic field, active length of the converter, current flow through the conductors, all these three are the reasons that is on which the torque developed can be dependent. So all the above factors will be the answer here. So here you can see all the above factors is the answer for this. Then we'll go to question number 100. For starting a DC motor, a starter is required because it limits the speed of the motor, it limits starting current to a safe value, it starts the motor, none of the above. So for starting a DC motor, a starter is required because it limits the starting current to a safe value. That condition is taken into consideration, and because of that, a starter is used. So option B will be the right answer here. It limits the starting current to a safe value. So here you can see option B is the right answer for this question. Thank you, students.